The last speaker for this morning is Mark Schellis from Nijmegen, who's going to talk about comms, causality, and contractions in atomic Markov categories. Please.
Indeed, thank you. So hello everyone, and welcome to this presentation titled Combs, Causality and Contractions in Atomic Markov Categories. This is joint work with Dario Stein. And before I get into what we're actually interested in, I want to start with a brief historical overview of what preceded this paper, because we consider it as a refinement of several previous developments. So the first one is the PhD thesis of Houghton Larson from 2021, in which he worked in a setting of semi-Cartesian monoidal categories, assuming universal dilations, which is a fairly strong property. And in that case, he defined the notion of a causal channel, and he hinted at the notion of trace for those causal channels, but he deliberately didn't go into that direction, so we kind of wanted to fill in that hole. The second prerequisite I want to mention is this paper about Coombs, in which they define different notions of Coombe equivalence, and they give some conditions on when different notions of Coombe equivalence coincide. So we will also generalize that result in there. And the last paper I want to mention by Fritz et al., or like all of these people, is the one that defines the atomicity axiom for Markov categories, which will be very crucial for our development. So for historical accuracy, I think I wanted to give a shout out. So what are we actually interested in are so-called contraction identities. So here is a simple instance of a contraction identity. So as you can see on the left, let's just look at the morphism with F1. You kind of can see from the structure of the string diagram that the information flow is organized in a way that to compute the output X, you don't need to use the input X. So ideally, I would want to be able to feed the output of type X to the input wire of type X and then kind of pull that wire together. That's what you can see on the right. And the question that we ask is, in which cases do these kind of identities hold? So if I have two different kind of factorization of a morphism, which we will later call non-signaling, then if I pull the wire together of equal wires together from equal morphisms, will this still be equal? And this is an instance of a contraction identity, which later I will give a formal definition of. But so first, okay, contraction identities always hold in trace monoidal categories. This shouldn't be too surprising. So as you can see on the left, I have my original morphism, but I took a trace of it. Now using the trace axiom, first I tightened it, then I applied yanking, then I applied the Markov category axiom of the copy being commutative. I managed to reduce to this thing, so it's easy to see then the contraction identity on the previous slide holds. But usually the Markov categories we are interested in are definitely not trace monoidal, so we want to give some other kind of condition. And we can see that contraction identities fail in certain Markov categories. For example, in Borel stock, which we have already encountered before, the category of standard Borel spaces and the Markov kernels between them. And there's a corollary of this immediately, because as we've seen, these contraction identities are always validated in trace monoidal categories, is which Borel stock cannot be embedded, by which I mean faithfully embedded into any trace monoidal category. Why do we carry my task? Like, you never wanted to do that in your life? Well, Combs and causality. So there was this paper by Jakobs, Kissinger, and Zanassi in 2021, in which they use solve a causal inference problem using string diagrammatic techniques in InfinStock. And for that, they actually used an embedding to a compact closed category of matrices with positive entries to be able to use the cup and cap structure that's available. I will later get back to this example when we talk more about Combs. But it is a priori not clear how we would do a similar thing for Borel stock. So this is really the question. If you want to do causal inference in Borel stock, then we don't have this method available. So we definitely care about this embedding. And now I will show why the contraction identity fails in Borel stock, and I will give you the idea of why it fails. It has to do with the atomicity axiom. So some minimal measure theory going on here. So I just take the unit interval and I take the Lebesgue measure on it, and I take two measurable predicates. One is the falsity predicate, one is the equality predicate. And let's see why the contraction identity fails, or here's why this fails. So what happens intuitively, if I sample from the distribution and compare it to any element in the unit interval, they have a 0 probability of being equal. So they are almost surely not equal. So as you can see in the reduction, then the two string diagrams here and here will be equal to each other, the thing in the middle. But if I pull the wires tight, again, just intuitively, the left will, of course, be constant 0. But on the right, I just take a sample from the distribution. I copy that sample, and then I compare if the sample is equal to itself, which it is. So you see that the contraction identity fails in Borel stock. Sad. So why does it happen? It is not atomic. So I claim that this is the source of the problem. And by using the atomicity axiom, which I will shortly recall, we will actually solve this problem for atomic Markov categories. Okay, what happens here next? Oh, a recap of Markov categories. So we have seen this today, so I will be very brief about it. A Markov category is a symmetric monoidal category where every object is equipped with a co-commutative comonoid structure. By that I mean there's a morphism copy, or by delta here, which goes from X to X tensor X, denoted like this. And there's a discard morphism, which goes from X to the tensor unit, such that all the co-commutative comonoid equations are satisfied. These are these three, and that the discard map is natural. So that implies that the tensor unit in Markov categories is a final object. So this is the setting that we are working in. Oh, it's there. And then we recall the notion of almost sure equality in Markov categories, which is, if you don't believe it, I can just tell that this is a generalization of the usual measure theoretic notion. So we say that F1 is P almost surely equal to F2 if this equation of string diagrams holds. So I think in earlier versions of the axiom, we didn't have the extra wire there. I think nowadays this is fashionable to put it there as well. So this seems to be a better notion. And then we can say that P is absolutely continuous with respect to Q if Q almost sure equality implies P almost sure equality. Okay, and now we are ready to finally recap the atomicity axiom. So first we say that the morphism P in a Markov category is atomic if copy after P almost sure equality. No, if copy after P is absolutely continuous with respect to P tensor P. So P tensor P almost sure equality implies copy after P almost sure equality. There's a graphical depiction of it if this seems a bit too complicated. So if we say that P is atomic if the equation on the right holds, then the equation on the left holds, then the equation on the right also holds. So what is the intuition behind this axiom? First, an example is, okay, I have to say that the Markov category is atomic if every morphism in the Markov category is atomic. And Finstock is such an atomic Markov category intuitively because the support of copy after P is contained in the support of P tensor P. In general, the relation between supports and atomicity is not this simple, but in this case, this really holds because this support inclusion holds. But then I claim that, for example, Bohrl-Stock is not atomic. And for that, we can see what are the atomic morphisms in Bohrl-Stock. And the Markov kernel from A to X is atomic if and only if it is completely atomic in the sense of measure theory. So what does this mean? The atoms of a measure are the points which have a mass. Is this written? It's written right. So with the points which have a mass, and I say that the Markov kernel is completely atomic if for all inputs A, the weight of the set of atoms is 1. And the Lebesgue measure is not completely atomic. In fact, it doesn't have any atoms. And then we can recap the previous counterexample that we have seen. So the idea is again very same. It's interesting. I think it's still visible enough. So on the left, we say exactly that if we take the Lebesgue measure tensor with itself, then the equality holds again, because if I take two independent samples from the measure and compare them for equality, they have a 0 probability of being equal. So this will hold. But on the bottom again, if I copy the sample and check with itself for equality, then we can see that they will always be equal, but the falsity predicate always gives me 0. So we see that formally this atomicity axiom fails in Bohrl-Stock. Okay. So let's recap some more notions before we can finally get to see why atomic Markov categories satisfy the contraction identities. So this is the standard notion of conditionals. I say that the Markov category has conditionals if every F can be factorized in this way. So this is really just a categorical generalization of conditional probability. I can first take one of the marginals, and from the marginals using the conditional probability, I can compute the other marginal. A Markov category has conditionals if I can do this for all the morphisms. And then there's another annoying technical property that we require in our developments, which is that the Markov category is cancellative if those implications hold. So if these equations where I discard the left input hold, then these should also hold. Our favorite Markov categories in general are not necessarily cancellative. So sets is not cancellative, Finstock is not cancellative if we put the empty set on that wire. Because if this is the empty set here, then this is just the empty function. And the two empty functions will always be equal to each other. We can usually resolve this problem by excluding these degenerate cases and just saying that the empty set is not included in our collections of objects, or we just assume cancellativity on the fly for certain wires. So this is not a real obstacle, but it's an important side condition of the theorem that will soon appear. So knowing that, we define non-signaling morphisms. And these are the class of morphisms for which we hope to define a notion of trace, which will lead to the contraction identities. So I say that F is non-signaling from the W input to the W output. Intuitively, if you compute the W output, I don't need the W input. So how does this string diagram encode this? If I discard the left output, then I might as well define the right input, and I can just have a morphism from X to W that directly computes W from X without using the W input. So this exactly means the existence of this factorization, that I don't need this input to calculate this output. And we say a morphism F is non-signaling if it admits such a factorization. And then now we will define a notion of trace for non-signaling morphisms. How do we do that? If a Markov category C has conditionals, we can nicely characterize all the non-signaling morphisms. All the non-signaling morphisms have a disintegration of this form. So this is the result that appears in our paper. And this is an if and only if. So if a morphism admits such a factorization, then it is known to be non-signaling. And now we can use this representation to calculate a trace. So how do we do that? I want to define this trace operation for F, where I assume that F is non-signaling. So like normally here would be an output, here would be an input, and I kind of want to form this feedback loop. So I take such a disintegration, which I know exists because F was non-signaling. And then like you can graphically see how I pull this wire tight. I will arrive at this, and this will be the definition of the causal trace. Okay, you might say, you can give me a different disintegration. I give you a different causal trace and we don't get anywhere. And normally this would be true, but if our Markov category is atomic, this is independent of the choice of disintegration. And I would say this is the most technical result in the paper. So this is from what everything follows. And the assumption of the atomicity is very important when we try to prove this kind of theorem. So this is not the case in any Markov category with conditionals. Okay, so what do we do with this? So this causal trace better satisfies some properties which resemble the trace monoidal category axioms. And in fact, they do. I will show you one example, so an analogy of strengthening, just to see how these propositions compare to the trace monoidal category axioms. So let's just look at the picture for a moment. If this was a trace monoidal category, the axiom would sound like these two things are equal, period. We do it a bit harder. So we say that if F is non-signaling, so F is traceable, then G tensor F is also traceable. Moreover, this equation holds. And for many of the other axioms, we also have this kind of one-directional implication. So we don't necessarily want to say that if this is traceable, this is also traceable, because this will not be true in general. But we always have this one direction of the implication, and we get a restricted version of the trace monoidal category axioms. Just for historical accuracy, this is weaker than the partially traced categories from Harvardian stock, if someone would think about those. Okay. Now, I will show that causal traces not only exist in atomic Markov categories with conditional, but also in free Markov categories. If you haven't seen free Markov categories over generators yet, all you need to know is they exist. They are kind of like categories of string diagrams, and we can nicely represent them by hypergraphs. If you've seen the hypergraph representation, this is for you. So string diagrams now look weirder. So this string diagram can be represented by this hypergraph. The idea is that these are the sort of the input ports where the data can go in. These nodes correspond to the wires, and the boxes and the hyper edges correspond to the boxes. And the idea is that I want to take the trace of this morphism. So I kind of want to glue these 2 points together. But first, I have to make sure that this is non-signaling. And there's a very simple condition to express that this morphism is non-signaling. I can just say that morphism in a free Markov category is non-signaling from a set of input ports to a set of output ports, if and only if there is no directed path from here to here. We can see that there is no directed path there. So we can just glue these points together, getting the causal trace. So what happened is there were 2 different points. I glued them together here. I removed one output port, and then I got the trace of this morphism. And this also satisfies all the causal trace properties. There's a bit more things going on. I didn't put it on the slides, but I can draw here maybe with the black, right? Or the blue icon, black. So if we were to take a trace of, let's say, this morphism where this is an X, this is an X, then I can clearly do this trace. But after this, I would need to normalize the hypergraph, right? Because this should be equal to this. This should be equal to this. So the combinatorics is a bit more complicated than just gluing here, but it all works out nicely, and I satisfy all the causal trace properties. Okay. And now the big thing, the big definition, we say that a Markov category C satisfies all contraction identities. What this is saying before I go into the formals is that if I have two morphisms in the category which are equal to each other, then it doesn't matter how I factorize these morphisms and then take the trace, the traces will still be equal. So formally what happens here is if I give an interpretation to boxes in the signature sigma, then I get a functor from this free Markov category to C. And then I say that if I take to any two non-signaling morphisms in the free Markov category, and I choose an interpretation of boxes, if the interpretation of these morphisms is equal, then the interpretation of the syntactic traces will also be equal. By this contra W, I mean the syntactic trace when I contract along W. And essentially, if we would go back to the beginning, the contraction identity I have shown is also of this form. And then the main result, which is really nice, is that if my Markov category is cancellative, atomic, and has conditionals, then all of the contraction identities are satisfied. Yeah, so what is this good for? Oh, I wanted to discuss the premises of this theorem for a moment. So I both assume atomic and conditionals, so you might ask whether they have to do something with each other. We have seen a category which has conditionals but is not atomic, Bottlestock. We also conjecture that there are categories which are atomic but do not have all conditionals, and we conjecture that the free Markov categories are such. We didn't manage to prove this, but we are almost sure of it, so to speak. Okay, but this is something for the future, but we are definitely interested in the information flow properties of free Markov categories. Okay, now I can go to Coombs. So on our Coombs, they've already mentioned like there was talk of lances. Apparently people here like it. So extensionally, I can just think of a Coombe as a non-signaling morphism drawn in a very evocative shape. So I kind of want to say that to compute this B output, I don't need the B prime input. So I just need to, I should be able to put a morphism in there. For more intentional definition, I could say that a Coombe is a pair of morphisms which have exactly the right types. And again, my aim with the Coombs is to put morphisms in that hole. And how do I do this? It's called Coombe insertion. And this is actually an instance of a causal trace. So if you see that I told that this is a non-signaling morphism, so to compute this output, I don't need this input. So if I draw C a bit more normal, you would see this kind of structure. And this is exactly a causal trace. So Coombe insertion, if I have causal traces, is really an instance of this. And then I can turn back to this causal inference paper, where they wanted to do exactly this. So they used Coombs for a causal inference problem in Finstock, but they wanted to do this Coombe insertion to be well-defined. So they made an excursion to a compact Loess category of matrices with positive entries. There they done this kind of stuff, which they can do because there's cups, there's caps, cups and caps. And then they proved that the result again lives in Finstock, so they get a stochastic matrix. This whole exercise now we know is unnecessary because we can just say that this is an instance of a causal trace. Finstock has causal traces, so I am free to form this kind of thing. So this maybe simplifies the formalism of causal inference problems in this manner. Okay. And to conclude, before we all have lunch, I have something to say about Coombe equivalence. So this is from a paper by Hefford and Comfort. I think they will be referred to on the next slide, that I have 3 different ways to say that Coombes are equivalent to each other. The first one is the simplest and most elegant, in my opinion, is that their extensions are equal. So how do I get the extensions? I just insert the swap map. So this is called extensional equivalence. I can also have that they are contextually equivalent, which means that all Coombe insertions are equal. And then I also have this optic equivalence, which looks a bit scary for people not friendly with coens like me, but it's actually just quotienting under this equivalence relation by sliding. So I say that if they are identified by the equivalence relation generated by all of these slidings, so here this H belongs to the lower part of the Coombe, here it belongs to the upper part of the Coombe, and then they are optically equivalent. And general results from Hefford and Comfort is that there's a chain of implications. Optic equivalence always implies contextual, always implies extensional. But they also show that all 3 notions of this Coombe equivalence coincide in compact Loess categories and Cartesian monoidal categories. Now there's more to it. Thanks to us, we say that if a category has causal traces, then the extensional and contextual Coombe equivalences also coincide. And if we also put throw universal dilations in the mix, if you know what they are, then that implies that all notions of Coombe equivalence coincide. So specifically in Finstock, the category for finite discrete probability, all 3 of these notions coincide. So that is pretty nice. Okay, so at this point, I think I will wrap up. So what did we achieve? We refined several previous works and defined the notion of a causal trace, and show that if they exist in Markov categories, they imply all contraction identities. So this is really a strong addition to the equational theory of Markov categories. We recognize the role of the atomicity axiom in this theory of causal traces. And using the existence of causal traces, we gave you sufficient conditions for equivalence of Coombe equivalences, maybe like there's a better phrasing, in Markov categories. Oh, these last 2 points are kind of the same. Sorry about that. Then I would like to thank you for your attention. And if you have any questions, feel free to.
Okay, thank you very much. There is a question, Alex, please.
Thanks for the talk. So it seems like if you effectively embed and trace category, it's probably sufficient to have causal traces.
Exactly.
Can you say anything about the converse?
So if
you have causal traces, you have a fake that you do something like a construction or not.
I haven't thought of it, so maybe I would refer the question to Dario immediately. But I think we haven't thought of this right now.
Future work, we'd love to know. So, the free Markov category is one of these things where, I mean, it doesn't have a trace, but can you embed it? Where would you embed it? Probably into a free hypergraph category. So that should work, but
The framework seems like it should be fine.
Wasn't there some problem with that?
yeah. So if we understand that case, then that will show the way to large conclusion.
Right, any more questions?
Everyone's hungry.
Right, seems not so. Let's take our speaker again.